Okay, let's talk about finding the equilibrium pressure when two gases mix. Here's the problem we are looking at. Imagine we have a container split into two parts by a wall that's a thermal insulator. The first chamber, let's call it V1, has a volume of 2 liters. It contains N1, which is 5 moles of an ideal gas at a pressure of P1, which is 1 atmosphere. The second chamber V2 is 3 liters and holds N2 4 moles of ideal gas at a pressure of P2 2 atmospheres. Now the wall separating them is removed, allowing the gases to mix and reach a new balance. We want to find out what the final equilibrium pressure of this mixture will be. And we have a few options here. 1.8 atmospheres, 1.3 atmospheres, 1.6 atmospheres, or 1.4 atmospheres. Let's figure this out. So, the first thing we need to do is just clearly identify everything we are given right at the start. We have our initial conditions for each chamber. For chamber 1, we know the volume V1 is 2 liters, the number of moles N1 is 5 moles, and the pressure P1 is 1 atmosphere. Then for chamber 2, we have the volume V2, which is 3 liters. The number of moles N2 is 4 moles, and the pressure P2 is 2 atmospheres. Just listing these out helps keep everything clear. Next, let's think about the final state. Once that partition is removed, the gases mix together and settle into equilibrium. The total volume of the combined system will just be the sum of the two initial volumes, V1 plus V2. So that's 2 liters plus 3 liters, giving us a total volume of 5 liters. Similarly, the total number of moles of gas will be the sum of the moles in each chamber N1 plus N2. That's 5 moles plus 4 moles for a total of 9 moles. In this final state, we'll have a new equilibrium pressure which we are calling P final and a new equilibrium temperature T final. Our goal is to find P final. To solve this, we'll use a couple of fundamental principles. First, the ideal gas law, which describes the state of an ideal gas. Second, because the system is insulated, the total internal energy is conserved. For an ideal gas, internal energy depends on the number of moles, the constant volume specific heat capacity, and the temperature. Applying conservation means the sum of the initial internal energies of the two chambers equals the final internal energy of the mixture. Assuming both gases are the same type, the specific heat cancels out. This simplifies the expression significantly, giving us a key equation relating the initial moles and temperatures in each chamber to the final temperature of the combined gas. Now we need to figure out those initial temperatures T1 and T2. We can get these from the ideal gas law PV equals nRT. If we rearrange that, we find that the temperature T is equal to PV divided by nR. So for chamber 1, the initial temperature T1 is equal to P1V1 divided by N1R. And for chamber 2, the initial temperature T2 is equal to P2V2 divided by N2R. We don't need the value of R itself, just these expressions. Alright, let's use these expressions for T1 and T2 and plug them back into our conservation equation. N1T1 plus N2T2 equals the total moles times T final. Substituting T1 and T2 gives us N1 times the quantity P1V1 over N1R plus N2 times the quantity P2V2 over N2R. This whole thing equals N1 plus N2 times T final. Notice how the N1 term in the first part cancels out and the N2 term in the second part cancels out. We are left with P1V1 over R plus P2V2 over R equals the quantity N1 plus N2 times T final. We can factor out the 1 over R on the left side, giving us the quantity P1V1 plus P2V2, all divided by R equals the quantity N1 plus N2 times T final. Now we can solve for T final. T final is equal to the quantity P1V1 plus P2V2, V2 divided by the quantity N1 plus N2 times R. So we found an expression for the final temperature. The final step is to find the equilibrium pressure. We start by applying the ideal gas law to the final state of the mixture. We substitute in the total volume as V1 plus V2 and the total moles as N1 plus N2. Next, we substitute the expression we just found for the final temperature into this equation. Notice that the term N1 plus N2 times R appears in both the numerator and denominator on the right side. These terms cancel out nicely. This leaves us with a simpler equation. Finally, we divide by the total volume to isolate the final pressure. This gives us the formula for the equilibrium pressure based on the initial pressures and volumes. Now it's time to plug in our numbers and calculate. Using the formula P final equals P1V1 plus P2V2 divided by V1 plus V2. We substitute the values P final equals the quantity 1 atmosphere times 2 liters plus 2 atmospheres times 3 liters, all divided by 2 liters. In the numerator, 1 times 2 is 2 atmosphere liters plus 2 times 3 is 6 atmosphere liters. So the numerator is 2 plus 6, which is 8 atmosphere liters. The denominator is 2 plus 3, which is 5 liters. So P final is 8 atmosphere liters divided by 5 liters. The liters unit cancels out, leaving us with atmospheres. 8 divided by 5 is 1.6. Therefore, the final equilibrium pressure P final is 1.6 atmospheres. So the equilibrium pressure of the mixture is 1.6 atmospheres. Looking back at our options, this corresponds exactly to option number 3. Our final answer is indeed 1.6 atmospheres. Nicely done!